And here we are in part 3 talking about division using long division and part 10 about functions. So let's remember how when you divided in, I don't know, 4th grade, a number like, for example, 12 divided by 5, you would set it up this way and then say 5 goes into 12 2 times, and you would write it here, and then you would check 2 times 5 is 10, you would subtract this and you would get 2, which means the 12 divided by 5, it's actually 2 remainder 2. Or we could write the and where this is called dividend, this is called divisor, this is called quotient, and this is called remainder. So we could write it 12 equals 5 times 2 plus 2. So this is just from grade school. Now let's try to do this using polynomials. So if we had to divide x to the third minus 7x to the second plus 2x plus 1 by x minus 3, the yellow one would be the dividend and x minus 3 would be the divisor. So following the same pattern as when you divide whole numbers, let's take the first term, x to the third, and divide it by the first term, x. So x to the third divided by x, it's x to the second. Now let's check by doing x squared times x, it's x to the third, and x squared times negative 3 is negative 3x to the second. And as you see here, we subtracted the 2 that we got. So basically, we are going to subtract. So when I subtract, I change all the signs here, and we are going to obtain, this cancels, negative 4x squared plus 2x plus 1. Now this is our new dividend. So we're going to divide again the first term by the first term that we had here. So negative 4x squared divided by x is negative 4x. And now again, we check by multiplying negative 4x with each of these terms. So when we divide only by the first term, but when we multiply back in, we multiply both terms. So negative 4x times x is negative 4x squared. Negative 4x times negative 3 is plus 12x. And again, we subtract. When we subtract, we change all signs. So plus and minus. Now these two give us 0. They always have to give us 0. 2x minus 12x is negative 10x plus 1. Now this is the new dividend. So let's divide the first term by x. So we get negative 10. And now again, we multiply negative 4x by each of them. So we get negative 10x plus 30. And again, we subtract. Let me clean this up. So we get plus and then minus. And we end up with negative 29. So the solution is x squared minus 4x minus 10. This is the quotient, and this is the remainder. So this is quotient, and this is remainder. So basically, x cubed minus 7x squared plus 2x plus 1, if we would write that, x cubed minus 7x squared plus 2x plus 1 over x minus 3 can be written as x squared minus 4x minus 10 plus the remainder negative 29 over x minus 3. We can write it mathematically this way. And finally, let's talk about functions. So I chose here 6 functions that show up in calculus, but I wrote the parent function. So from here, they are you can produce all kinds of combinations. And for each function, I'm going to discuss domain, intercepts, if it's even, odd, or neither, and some transformations. So let's take a look at the first function, f of x equals x. So if we take a look at just at the first one, I made the graph. The graph, you can make it by giving values, or you can just put it in the calculator and you see that you have something like this. So the domain of this function, it's actually from negative infinity to infinity. There is no restriction, there is no gap, there is no break into the graph. So that's why the domain is negative infinity over infinity. Now this is the type of function that is called polynomial. So for a polynomial function, this is the domain all the time. Now the intercepts, we notice that this graph intersects the x-axis at the origin and the y-axis at the origin as well. So the x-intercept, it's at 0, 0, and the y-intercept at 0, 0 as well. This function is odd because it's symmetric with respect to the origin. So if I have a point from here, it has a symmetric point on the other side of the origin. A point from here will have a symmetrical point on the other side. So this is an odd function. Now transformations, if I make a function of this form, f, like for example, let's call it f sub 1 of x equals x plus 1, what it means, it's actually the same function shifted 1 unit up. So every point is going to go 1 unit up. And so if we connect them, we are going to get actually the graph of x plus 1. X minus 1 would be shifted down, and so on. Let's take a look at the second function, g of x equals x squared. Again, when we take a look at this function, the domain, so the values of x, the x values, we can take anything, any x value, so the domain is negative infinity, infinity. The intercepts, this graph intersects the x-axis and the y-axis at the origin. So 0, 0 is the intersect. This function, it's even because a point from the graph, it's symmetrical with respect to the y-axis, or if we fold this graph by y-axis, the two sides are going to overlap. So this one was odd and this one is even. And if we do a transformation, for example, if we write g1 of x as x minus 2 squared, what happens to this function, it's actually shifted 2 units to the right. Because of this minus 2, we shifted 2 units, and so everything is going to be shifted 2 units, and the graph would look something like this. Now if we put a plus 3 as well, then this blue graph is going to shift 1, 2, 3 units up, so the graph would look something like this. Let's take a look at h of x equals square root of x. So the graph is here, it's this curve, it starts at the origin. So the domain now is going to be 0 to infinity. Why it's 0 to infinity? Because there is no graph on this side of the y-axis. 0, it's bracket, it's included because I can have square root of 0. That's 0. The intercept, again, the origin, when x equals 0, h of 0 equals 0. So the origin, and if h of x equals 0, x equals 0. So the origin is the x-intercept and the y-intercept. This function is neither nor even nor odd. And transformations, if for example we come up with h1 of x equals square root of x minus 1, it means we are actually shifting this 1 unit to the right. So it would give us something like this. If we were to have h2 of x equals square root of x plus 1, we would shift 1 unit to the left. So we would get something like this. Now, when we have these shifted functions, then the domain changes. So the domain for the red one would be from 1 to infinity. The domain for the blue one would be -1 to infinity. So something to remember, when we have square root of an expression, in order to find the domain, we have to set the expression to be greater than or equal to 0, always, to find the domain. Okay, now let's take a look at d. d is the function I of x equals cube root of x. So we have the graph. We see that this graph extends on the whole number line, right? So then the domain would be -infinity to infinity. What does that mean? It means that under the radical we can put any numbers we want, because cube root can be computed of negative numbers and positive numbers. This graph is symmetrical with respect to the origin, so this function would be odd as well. And we have also the intercepts at the origin. This graph intersects the x-axis and the y-axis at the origin. And transformations, well, if I have, for example, I1 of x equals cube root of x plus 2, we would have to shift it 2 units to the left, and so the graph would look something like this. Okay, let's take a look at so basically what I'm trying to say in this problem, no matter, and here the domain wouldn't change, right? We can put any number, so the domain would be -infinity, infinity. Now let's take a look at problem E. J of x equals 1 over x. So the graph, it's showing us that there is a problem when x equals 0, right? So when x equals 0, the graph was broken down into 2 pieces. So the domain would be -infinity, 0, union 0, infinity. So at the 0, we have open parentheses because x cannot be 0. We have no intercepts, and our function is symmetrical with respect to the origin, so this would be an odd function as well. Now, something that I want to discuss, if we have combinations of this function, is, for example, we have j sub 1 of x equals 1 over x plus 3. What would change with the domain? Well, x plus 3 cannot be 0. So in order to find the domain of rational functions, of functions that have a numerator and a denominator, we always set the denominator. If you want, we can set it equal to 0, and that will give us x equals -3. So all the numbers, all the real numbers are in the domain except -3. So the domain would be -infinity, -3, union -3, infinity. So the graph would be shifted 3 units to the left, so it would look something like this. And 3 units. Okay, and let's take a look at the last one, another popular function, which is absolute value of x. So the domain, when we look at it, it has no restrictions, so -infinity, infinity. This function is symmetrical with respect to y, so it's even. Again, it intersects at the origin. They have the x-intercept and y-intercept at the origin. And if we have k sub 1 of x equals absolute value of x minus 2, we would have to shift it 2 units and get this function as our transformation function. Now, would that change anything to the domain? No, it will not. Well, there is a lot that can be said about functions, but we'll stick just to these ones for now.